Okay, now I want to attack our friend projectile motion. And show that the work energy theorem is consistent with what we already know. So I'm going to take a projectile that gets launched at angle theta with respect to the horizontal and launched at v0 and calculate everything old school and then show that in one line we get it new school with the work energy theorem. Okay, so my isolation diagram, mg, coordinate system, xy. So if I consider in the x direction, I had the sum of the forces, which is 0, is equal to ma in the x direction. So x double dot is 0. That is no acceleration in the x direction. So I now integrate from 0 to t. Okay, on the left, it's clearly just an antiderivative. I integrate and I get x dot at t minus x dot at 0 is equal to the integral of 0, or the definite integral of 0. In other words, x dot is a constant v naught x, which from the initial condition is v naught cosine of theta. Okay, so I can integrate again. And get what you fully expect, x minus x naught. I'm going to take x naught to be 0, and maybe I should make it very explicit. This is x at time t. Is equal to v naught. I'm going to slide the t in so it doesn't look like it's part of the argument to the cosine function. V naught t cosine theta. Not a surprise. We knew this. Over here, we have the sum of the forces in the y. That's minus mg is equal to my double dot. And with your kind permission, we'll integrate with less writing. So we get that y dot of t is equal to vy naught minus gt. What's vy naught? Let's see. That's this component. So that looks like the opposite. So that's sine. So I would have v naught sine theta minus gt, which we integrate again to get y of t is equal to v naught t sine theta minus 1/2 gt squared. Okay, so that is what we did before. That's getting everything as a trajectory parameterized by the time. But suppose instead I want to know how fast is the particle going at any particular height? Can I get that out of this solution? So let's try. So how fast, maybe I should just say, what about the kinetic energy as a function of y? Okay, so the kinetic energy will be 1/2 m vx squared plus 1/2 m vy squared. This is going to get ugly, but that's okay. So here's the x component of velocity. So this is 1/2 m v naught cosine theta squared, and that doesn't care about the time. But the y velocity does. It is, from here, v naught sine theta minus gt, which I now have to square. Well, at least I have a common 1/2 m, so I'm going to pull that out. 1/2 m v naught squared cosine squared theta. And now we have to multiply this one out, plus v naught squared sine squared theta. Cross term is going to be minus 2 v naught sine theta gt, and then plus gt squared. G squared t squared, excuse me. And close bracket. Just for tidiness sake. Okay, so that looks like it should simplify a little bit. I have v naught squared by the Pythagorean theorem. And I now have to try to figure out some way of expressing this junk as y. Well, y of t is here. So v naught sine theta times t. So apart from the 2 and the g, that term is looking pretty good. So let me see. If I pull out, so this is minus 2g times v naught sine theta. Okay, I pulled out a 2 and a g, but I don't have a 2, so I need a half. I pulled out 1g, so I have 1 left, and I have gt squared, right? There should be a t in there. There definitely should be a t in there. Thank you. All right, so the stuff in the square brackets in that line, is that, yeah, that is the same thing as y. Okay, so we end up with the kinetic energy is 1/2 m v naught squared minus, let's see, so the half and the negative 2 go out. I have an mgy minus mgy. Did that work? The peanut gallery is amused. All right. So, boo. Okay, so if I only care about position, what's the speed at a particular position, the work energy theorem is going to be my friend. It's going to make it tough to know how long it's going to take to get somewhere, but it makes it really easy to figure out what's going on as a function of position. I actually want to rewrite this. The kinetic energy plus mgy is equal to 1/2 m v naught squared. That's a statement that k final plus u final is equal to k initial plus u initial, where I'm measuring my gravitational potential energy from what point? Yeah, where the projectile started. So from this origin there. Exactly. Okay?